Section: Introduction. In this paper, we're diving into the challenge of tweaking large language models so they produce the kind of results we want, like being useful, safe, accurate, or creative. We're exploring a two-step method where we first figure out what good outcomes look like based on what people prefer, and then we adjust the language model so it's more likely to give us those good outcomes. We're particularly focused on two big questions in this process. 1. When we're trying to make the model's outputs align with what humans like, we use a reward model based on human preferences. But, is there a way to tweak this reward model to make the alignment even better? 2. Often, we want the model to have several good qualities at once, like being helpful, safe, and accurate. If we have different reward models for each quality, how do we combine them effectively? One of the tricky parts is that there's no clear-cut goal for alignment, making it hard to decide the best way to adjust or combine these reward models. Our big idea is to look at alignment through the lens of probability. Essentially, we're trying to get the model to produce results that are likely to be seen as good for a certain quality or for multiple qualities at once. To put this into action, we need to define what good means. In the context of rewards based on what people prefer, a good outcome is one that scores higher than a certain benchmark specific to the prompt. Our first major finding is that when we learn what good outcomes are from people's preferences using a specific statistical model, the Bradley-Terry model, and then adjust the language model to aim for these good outcomes while keeping it similar to its original form, the best way to tweak the reward model involves using a specific mathematical function, the sigmoid function. This approach not only helps in making the model focus on improving where it's not doing well but also prevents it from exploiting loopholes in the reward model. Moreover, this method of tweaking rewards gives us a straightforward way to combine different reward models. By adding together the adjusted rewards, we can aim for outcomes that are good across multiple qualities. This combined approach can significantly enhance how well the model aligns with our desired outcomes. We also discuss the standard process of training language models to align with human preferences, which involves training reward models based on which of two responses people prefer and then adjusting the language model to favor responses that are likely to be preferred. This adjustment is done in a way that tries to keep the updated model close to its original version, to maintain the valuable information it has learned. In summary, our paper presents a novel approach to improving how language models can be adjusted to produce outcomes that align with multiple desired qualities, based on a probabilistic understanding of alignment and a strategic modification of reward models. Section Summary. The paper explores aligning large language models to bias their outputs towards desired properties, such as being helpful, harmless, factual, or creative. It focuses on the two-stage approach of learning a reward model from human preferences and aligning the language model to produce high-reward outputs. The main idea is to interpret alignment probabilistically, transforming the learned reward using a sigmoid function, which leads to practical benefits in encouraging the model to improve poorly performing prompts and in combining multiple reward models. Section: Reward Transformation. We're now going to discuss how we can change the reward system to better align with our goals. First, we need to clearly define what we're aiming for with this alignment. Essentially, we want to tweak the initial guidelines so that the outcomes are seen as good by people. To do this, we introduce a simple yes or no variable that tells us if a given response is good for a specific prompt. Our goal is to create a model that prefers responses that are considered good. We even refine this approach a bit to balance the rewards against other considerations. Using Bayes' rule, we can adjust the original model by increasing the weight of responses likely to be seen as good. We introduce a special parameter to control how much we adjust this weighting. This parameter helps us fine-tune the balance between sticking to the original model and aiming for good responses. Next, we need to figure out how to make a model that meets our alignment goal. This involves defining what we mean by a good response and how this definition affects the model's utility function. To start, we connect the idea of a good response to the utility function we're using for alignment. Then, we look at how to train the reward function using simple yes or no data for each prompt and response. This approach helps us learn a reward on a scale that makes sense for comparing different responses, similar to how certain models compare items based on preferences. However, when we consider pairs of responses instead of individual ones, things get a bit more complicated. We can't just apply the same transformation because the rewards for individual prompts don't translate directly to probabilities. Also, the reward model might not be clearly defined just from the data. But we can solve these issues by defining a good response as one that's preferred over a standard reference response. This way, we can adjust the reward model correctly. Looking at this from a practical perspective, the standard approach doesn't limit how much utility can increase for better responses, which can lead to exaggerated preferences for slightly better responses. By choosing a suitable reference response and adjusting the reward model accordingly, we ensure that the model's preferences are more in line with human judgment, especially when the differences between options are minor. This approach helps avoid overly dramatic shifts in preference based on the reward model, which might not always be reliable. Section Summary. The section discusses the process of reward transformation for aligning a model's generated samples with human-defined, good, properties. It introduces a binary variable indicating the goodness of responses and defines the alignment goal as producing a model that samples from the distribution of good responses. The transformation involves reweighting the base model by upweighting responses likely to be deemed good, and it aims to control the strength of this upweighting using a hyperparameter. Section. Choosing reference response. We're discussing how to pick a reference response and how to combine different rewards to guide a model's behavior. Let's break it down. Choosing a reference response. We treat the reference reward as a key setting in our approach. Think of it as setting a benchmark or goal. Our method works by rewarding responses that are below this benchmark in a straightforward, linear way. But once responses surpass this benchmark, the rewards start to decrease. So, we need to pick a benchmark that is both ambitious and realistic, something that our model can achieve and where our reward system can accurately judge the quality of responses. A practical starting point we've found is to use the 85th percentile from our initial set of examples. This means we look at all the responses we have, sort them by quality, and pick the value that's better than 85% of them. We'll explore more examples in the experiment section. Reward aggregation. When we're dealing with multiple aspects of a model's performance, like wanting it to be both helpful and harmless, we need a smart way to combine these different goals. Alignment goal. First off, we define our goal clearly. We want our model to score well across all the important aspects we're focusing on. For instance, if we're aiming for the model to be both helpful and harmless, we need to ensure it meets both criteria. We use a binary approach to measure this, essentially asking for each response, is this good for what we're aiming for? And we combine these using a logical AND, meaning a response is only considered good if it meets all our criteria. How to combine rewards. Following our set goal, we look at how to best combine individual rewards to guide the model. This isn't straightforward because each reward gives us information about one specific aspect, and simply looking at them individually might miss how they interact. We assume that we can evaluate each aspect, like helpfulness or harmlessness, independently based on the context and response. This means we believe we can judge if a response is helpful without it affecting our judgment on whether it's harmless, and vice versa. Mechanistic interpretation. We approach combining rewards with a probabilistic mindset, similar to when we're dealing with a single reward. A basic method is to add up all the rewards, adjusting their importance as needed. However, this simple sum can be misleading because a high score in one area might compensate for a low score in another, which isn't what we want. We illustrate this with an example where we prefer responses that are good in both helpfulness and harmlessness over those that are only good in one. We find that using transformed rewards, which adjust the importance based on our benchmark, leads to a preference for responses that meet all our criteria. Experiments. We then test our approach by aligning large language models, LLMs, to be both helpful and harmless using our method. Our experiments show that this approach helps avoid common pitfalls like reward hacking, where the model finds loopholes to score high without truly meeting the goals, and reward underfitting, where the model doesn't fully learn to meet the goals. By aligning models to the sum of transformed rewards, we effectively guide them to meet all our criteria, leading to significant improvements. Experimental setup. We follow a standard reinforcement learning from human feedback (RLHF) process, using specific datasets for helpfulness and harmlessness. These datasets include dialogues where we have to choose between two possible responses from the AI, with human feedback indicating the preferred one. We train a reward model for each aspect, helpfulness and harmlessness, and then fine-tune a policy model to align with our goals, using a large model pre-trained on instructions. Section Summary. The section discusses the selection of a reference response and the reward aggregation process for aligning multiple reward models. It emphasizes the importance of setting the reference to a value representing a good response achievable by the model and the use of utility transformation to align models to be good on all target properties. The experiments demonstrate that aligning to the transformed sum acts as aligning to logical and, leading to substantial improvements in language models aligned to the transformed reward. Section RLHF Setup. In our setup for reinforcement learning from human feedback, RLHF, we follow a common approach by optimizing for the best outcome while keeping a check on how much we deviate from our original plan, using a method called proximal policy optimization, PPO. We adjust the strength of this check, known as KL regularization, across various levels for each utility function and dataset. We run our experiments for 86 steps, which is enough time for our models to learn and adjust properly in all scenarios. We found that changing the way we calculate rewards helps in aligning our models better. By focusing on improving answers that initially receive lower rewards rather than those already scoring high, we aim to reduce instances where the model might try to game the system for higher rewards, reward hacking, and also pay more attention to responses that are not fitting well, underfitting. When it comes to choosing a baseline reward, for harmlessness, it's pretty straightforward. A simple response like, "I can't answer that," is considered good enough. We use variations of this response as our baseline reward in our experiments. However, for helpfulness, such a standard response won't work. Instead, we look at 64 different responses from the SFT model for each prompt and estimate a reward level that 85% of these responses do not exceed. This estimated level serves as our baseline reward for helpfulness. By aligning our models to these adjusted rewards, we expect to see a reduction in reward hacking and underfitting compared to when aligning to the original rewards. Our goal is to achieve better performance over the SFT model, and we have two ways to measure this. First, we train a large T5XXL model using the same data but with a different objective, which serves as a stand-in for true preferences. We consider it a win if our aligned model's response is better than the top 85% of SFT model responses for helpfulness, and better than the top 95% for harmlessness. Second, we use a method where we ask a PaLM-2 medium model, which has been trained on instructions, to choose between a response from the SFT model and one from our aligned model based on helpfulness or harmlessness. Our findings show that models aligned to the adjusted rewards perform better across the board. We also observed that aligning to the adjusted rewards uniformly improves the distribution of rewards. This means we see fewer instances of very high or very low rewards, indicating less reward hacking and underfitting. We confirmed this by comparing the reward distributions of models aligned to the original and adjusted rewards, using the same prompts and adjusting for differences in KL. Lastly, we looked at how adjusting rewards affects the model's tendency to take shortcuts, which are easy ways to get high rewards but don't necessarily lead to better responses. For example, models aligned to the original rewards might format their outputs as lists for helpfulness or suggest consulting a professional for harmlessness. Our analysis shows that models aligned to the adjusted rewards are less likely to use these shortcuts, indicating a more genuine improvement in alignment. Section Summary. The section describes the RLHF setup, where proximal policy optimization, PPO, is used to optimize expected utility subject to a KL penalty. Reward transformation is proposed to encourage alignment to focus on improving lower reward responses and reduce reward hacking and underfitting. The choice of reference reward is discussed, and aligning to the transformed reward is shown to dominate aligning to the raw reward, leading to uniform improvement of rewards and reduction of shortcuts such as formatting outputs as lists and suggesting consulting professionals. Section: Reward Aggregation. We're now focusing on our second objective, which is to combine rewards for various distinct goals. To achieve this, we aim to make a large language model, LLM, both helpful and harmless. In our further experimental setup, we specifically use reinforcement learning from human feedback, RLHF. Here, we train reward models for tasks related to being helpful and avoiding harm, as previously discussed. For the RLHF training, we only use prompts from the dataset focused on helpfulness. This choice stems from the observed conflict between being helpful and avoiding harm, which led to a preference for more helpfulness prompts over harmlessness ones in previous studies. The policy model we use is the same as the one in our single reward experiments, which was fine-tuned on helpfulness data. All other training details remain consistent with those single reward experiments. Additionally, we explore a method called best-of-3 sampling. This involves drawing 3 samples from the fine-tuned model, ranking them by their combined reward, and choosing the top-ranked sample. This method is another way to align the model, where best-of-3 sampling slightly diverges from the original policy but results in samples with a higher expected reward. In our tests, we gradually increase the number of samples from 1 to 191. We're motivated to try best-of-3 sampling for 2 reasons. It shows that our reward combining method can be applied beyond RLHF, and it simplifies the process by avoiding complex optimizations, allowing us to focus on the impact of choosing the right reward. For our baseline method, we use a weighted sum of the raw rewards, testing 97 different combinations and reporting the ones that perform best according to our evaluation metrics. When it comes to combining rewards, we simply add them together. Choosing how to weight this addition isn't straightforward, so instead, we use reference values for each reward. Intuitively, setting a lower reference value for one reward makes it saturate more easily, shifting the optimization's focus to the other reward. For best-of-3 sampling, using 98 different reference values gave us the best baseline performance. We aim to make the reference rewards for helpfulness and harmlessness comparable, using the estimated median from the fine-tuning as a lower reference, which prevents premature saturation when optimizing both goals simultaneously. For RLHF, setting the reference reward for helpfulness slightly higher, at the estimated 75th percentile, showed the best results, though further tuning could potentially improve this. Our evaluation metric is designed to reflect a logical and condition, meaning a generation is considered successful if it scores higher than the median for both helpfulness and harmlessness from the fine-tuned model samples. Combining transformed rewards should be better than the baseline method for 2 reasons. It aligns with the logical and condition, and it helps avoid over-optimizing for a single reward, as seen in single reward cases. Our results show that using both rewards for alignment, whether through best-of-3 sampling or RLHF, significantly improves over the fine-tuned model. The improvement is especially notable in best-of-3 sampling and in RLHF alignments with low divergence from the original policy, where there's minimal reward manipulation. This suggests that the main advantage comes from the logical and effect. In situations with higher divergence, the transformed reward method greatly outperforms the baseline, indicating a reduction in reward manipulation. Lastly, we directly examined whether the logical and effect is evident in the aligned LLM by looking at the distribution of rewards in the aligned policies. Our method leads to more balanced reward distributions, while the baseline method often results in one reward being significantly higher than the other. Interestingly, best-of-3 sampling and RLHF show different reward distributions initially, but our combining method consistently improves alignment in both scenarios. Section Summary. The section discusses the aggregation of rewards for multiple distinct goals in reinforcement learning. It explores the use of a transformed reward aggregation method, which aligns a language model to be both helpful and harmless, and compares it to a baseline method. The transformed reward aggregation method is shown to outperform the baseline method, leading to more balanced reward distributions and improved performance in aligning using both rewards for both best of 3 and RLHF setups. Section: Discussion and related work. We've been exploring ways to improve how AI systems learn from rewards, specifically aiming to prevent them from taking shortcuts or reward hacking in their learning process. This involves a variety of strategies such as averaging the outcomes from different models, setting limits on the optimization process, adding regularity to the reward models, continuously gathering human feedback, and addressing biases in the data. These methods can work well alongside the new transformation technique we're discussing, and they can even be combined for better results. In the realm of aligning AI models with multiple goals, a popular method has been to merge individual reward models using a weighted sum. Some researchers have suggested setting a limit on the rewards and tackling this as a constrained optimization problem, though this requires accurate baseline information. Others have looked into adapting social welfare concepts to balance diverse individual preferences, which is a bit different from our aim of meeting all set criteria. There's also been work on training a single reward model with data aimed at making the AI helpful and harmless, but this approach faced challenges with the model taking shortcuts in being harmless. By adjusting the mix of data used for training, these issues were somewhat mitigated. Our approach of transforming and then summing rewards helps avoid these problems. Our transformation technique is particularly useful for any alignment strategy that focuses on maximizing expected benefits. There are also alignment methods that directly use preference labels without creating reward models. However, if we're trying to align with multiple goals, we still need to combine these models to rank the outcomes. Our experiments show that transforming rewards can significantly improve results even in this scenario. Additionally, the importance of having a bounded utility function is highlighted, and our work contributes to this area by maintaining the traditional utility maximization approach while incorporating these new insights. A future area of exploration could be to see if using transformed rewards directly in the alignment process is more effective than just ranking options. For predicting reference values, we aim to forecast various reward levels for different scenarios. Instead of creating separate models for each level, we assume a normal distribution of rewards for each scenario. With this assumption, we use two models to predict the average and variability of the rewards. To estimate a specific reward level, we use a formula that includes a scaling factor related to the desired level. The training data for these models comes from generating and scoring multiple responses per scenario. In evaluating our models, we use a method called zero-shot prompting with the PaLM 2 model to compare outcomes from our aligned model and a standard policy model, asking which is more helpful or harmless. To avoid bias, we test each scenario in two different orders and decide the winner by majority vote. Lastly, in our efforts to identify shortcuts the AI might be taking, we looked at how the AI responds to tasks aimed at being helpful or harmless. For helpfulness, we noticed it tends to list responses, while for harmlessness, it starts repeating similar answers as it tries to avoid making mistakes. By analyzing the AI's responses and identifying common themes, such as suggesting professional help, we can pinpoint where it might be taking shortcuts. In summary, our work contributes to the ongoing efforts to make AI systems learn more effectively and ethically, by introducing new strategies for reward transformation and alignment, and by refining the methods for evaluating and improving these systems. Section Summary. The section discusses various techniques for mitigating reward hacking in the RLHF pipeline, such as reward model averaging, constrained optimization, reward model regularization, iterative human preference collection, and data bias mitigation. It also mentions alignment methods that use preference labels directly without explicitly instantiating reward models, and proposes a transformation technique that is relevant to any alignment strategy that explicitly maximizes an expected utility. Additionally, it outlines the implementation for reference value prediction and the evaluation details for POM2, as well as heuristics for shortcut discovery in the helpfulness and harmlessness tasks. Section RLHF Training Details. We use a technique called Proximal Policy Optimization, PPO, to align our training with reinforcement learning from human feedback, RLHF. To fine-tune our approach, we experiment with 25 different settings, aiming to achieve various levels of alignment, which we measure using something called KL values. These values help us understand how much our policies, or strategies, have changed. Instead of just picking these settings randomly, we use a special method to guess which settings will give us the results we're looking for, even though these guesses don't follow a simple pattern. Interestingly, when we want to achieve a specific level of change, measured by KL values, we find that we need to use less strict control if we first transform the rewards our model receives, compared to when we use the rewards directly. This makes sense because transforming the rewards helps prevent the model from hitting a point where making further improvements becomes very difficult. In our experiments, we show that when we match policies based on their KL values and apply this reward transformation, the improvements are more evenly spread out. This is better than just using the raw rewards, which can lead to uneven or excessive optimization for certain responses. We also notice that when we simply add up the raw rewards for different aspects, like how harmless or helpful a response is, the model might try to game the system. For example, it might produce responses that score very high on being harmless, even if that means the overall helpfulness takes a hit. This problem becomes even worse when the model tries to maximize its helpfulness score by exploiting weaknesses in how we measure helpfulness. However, when we use transformed rewards instead of raw rewards, these issues are significantly reduced. This is because transforming the rewards helps to focus improvements across different areas without letting any one aspect dominate due to the scoring system. We also find that transforming rewards leads to a more focused distribution of improvements across different KL values, compared to using raw rewards. This means that the improvements are more targeted and consistent. Lastly, we report on how well our aligned policies perform in tests. We compare them against a random selection under a specific setting, POM2, and against certain benchmarks for helpfulness and harmlessness. We also provide additional evaluation results to give a clearer picture of our findings.